a signature circuit. Okay, the absence of storage elements, that is what is a true hallmark of a combinational circuit, right? All right. So in the class, I think you have heard about single circuit faults, multiple circuit faults, and so on, right? Guys,
Yes,
have
sir.
you? Okay. So tell me, what is a multiple circuit fault? Give me an example.
If either VDD or zero is stuck at more than one nodes.
No. Oh, okay. No, the answer I was expecting was, see, there are how many nodes here? A, B, C, D. Then you can label this E1 or something like this. Can be labeled E, E1, E2, E3, E4, then F, G, G1. Okay, so these are some of the nodes, right? So let me label them. So nodes are A, B, C, D. Then E is the output of the NOT gate. Then it branches into E1 and E2. Then that E2 branches to maybe E21 and E22, right? And then F, which is the output of the AND gate. Then maybe G is output of the NAND gate. Then G1 is the branch of that NAND gate output. The other one is already named Z, so we can leave it there. So in addition to that, X, Y, Z are also there. So how many nodes are there? We have 4 plus 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are 15 nodes here. So if you allow any one of them to be stuck at 0 or stuck at 1, right? Or maybe it is neither stuck at 0 nor stuck at 1. So each node can be in any one of the three states. So there can be how many possibilities are there? 3 to the power 15, correct? No?
Yes, sir.
Yeah. Out of them, only one is not faulty. That is when none of the nodes are stuck at 0 or stuck at 1. That is the good circuit. It doesn't have any fault. So there are 3 to the power 15 minus 1 minus 1 you know faults, which are called multiple stuck at faults. Okay. For example, A is stuck at 0 and B is stuck at 1. X is stuck at 0 and C is stuck at 1, and so on and so on and so on. Does it make sense?
Yes, sir.
All right. So these are the multiple stuck at faults. But this is too much, right? We can't possibly use this fault model. It is impractical. So what do we do instead? What is a better fault model to use?
Single stuck.
Single stuck at fault. How many? We have each line can be either stuck at 0 or stuck at 1. So there can be 30 single stuck at faults. So we can label them A0, A1, B0, B1, and Z0, Z1. Okay. So this 30 seems reasonable, right? But even this may be, for a very large circuit with maybe millions of nodes, even this list is rather large. So we would like to further cut it down. So in the class, I may have discussed that theorem called checkpoint theorem. What does it say?
Primary input and fan
Yeah,
out. branch.
Only the primary inputs and fan out branches. So after fault compaction, we only had to worry about A0, A1, B0, B1, C0, C1, D0, D1. Then we called this, I think, E1 or something like that. E1 0, E1 1. Okay. And then E2 0, E2 1. And then E2 1 0 and E2 1 1, right? And then E2 2 0 and E2 2 1. And what was the other one? G1 0 and G1 1. Okay. So, and then finally Z 0 and Z. So these are our faults worth considering. Now the number of faults is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I guess. Huh? And then 13, 14, 15, 16, 19. So around 19 or 20. Okay. So we have managed to reduce it further down to 20. We may be able to even reduce a further more little bit. So for example, B0 and C0, what are they? They are
Inputs of NAND gate.
yeah. But B0 is a stuck at zero fault at the AND gate input, and C0 is a stuck at zero input at the AND gate input. See, we cannot distinguish between them. So we will never be able to tell whether B0 has occurred or C0 has occurred. Correct, no? So if
Yes.
B0 occurs, the output of the AND gate will be 0. If C0 occurs also, it will be 0. Right? So we don't need to differentiate between B0 and C0. It doesn't matter. So we call those as equivalent faults. So we can reduce one of them. We can remove this. Okay. So we can get rid of this. Similarly, see, this was what this D stuck at 0 can be removed because we would have already considered the stuck at 0 here. So D stuck at 0 is also not required. Right. I suppose that's about all that we can do. Right. Others we have possibly, so we can possibly reduce it by another one or two like this. Right. Now that's about all, right? We have compacted it as much as we could. Now we have to go and find test vectors for each of these faults, right? So as I may have mentioned in the class, before we get into that ATPG, right, or what we call as test generation, right? So what may be worth doing is take some random patterns. Okay, let us take one random pattern. So one of you give me a random pattern.
1011.
Okay, try 1011, right? If I put a 1 here, the good circuit will produce a 0. And as a result, the output X will be 1. And this will be 0. So as a result, y will be 0. Right? And this will be a 1. And this also. Now this is how a good circuit will behave. Now these are the faulty circuits. A circuit with a A0 fault. How will that circuit behave? If A is stuck at 0, then this will change to 1, right? And as a result, y will change to 1. Okay? So that means A0, a circuit with A0 will behave differently than a good circuit, and therefore we can go ahead and detect it. We can say this is something that gets detected. You agree with me?
Yes, sir.
Yeah. Similarly, A1 won't help because it's already 1, so this fault is not activated. If I put a 1 here, A1 will not get activated, so it is no use. B0, again no use. Okay, B0 is not activated. B1 gets activated. So if I apply a 1 here, I'm sorry, if the faulty circuit causes a 1 here, then this will change to 1 and this will change to 1. So B1 will get detected. C1 no use because it is not going to get activated. And C0 we already eliminated because it is equivalent, so no need to worry about that. D1 is no use, right? D0 is already eliminated. What about E1 0? Okay, so this guess we call it as E1. If this becomes 0, right, it doesn't really help because we already have a 0 here. So the good and the faulty circuit will not behave any differently. Even 1, it will get detected because if this is stuck at 1, right, and this is 1, so x will change to 0. So as a result, even 1 will get detected. Similarly, what about I think we call this E2. If E2 is stuck at 0, that will cause this to become 0. This will remain 0, no big deal, and nothing will happen. So E2 0 is not detected. E2 1, on the other hand, if this gets stuck at 1, then this y will change. So E2 stuck at 1 will get detected. We call this E2 and this one as E2 0 and E2 1. If E2 0, if E2 1 is stuck at 0, it doesn't matter because it's already 0. In a good circuit also it is 0. On the other hand, if E2 1 is stuck at 1, it will get detected because y is going to change. So any one of the outputs, if it changes, okay, we can observe. Okay, and E2 to 0, I think we call this E2 2, right? So it's already 0, no big deal. Then E2 to 1. If this is stuck at 1, then this will change to 0. So Z will change. So this is detected. We call this G1. If G1 is stuck at 0, nothing will change because already this is 0. If G1 is stuck at 1, no big deal because it's already 1 here. Then Z0 will get detected. and Z1 we cannot detect. So the random vector 1011 will detect 1, 2, 3, 4, 5, 6, 7 faults. So its fault coverage, okay, so 1011 detects 7 out of how many? We had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15,
Mm.
16, 17, 18. So 7 out of 18 faults. So its fault coverage is 7 by 18 times 100. So you can see that a random vector was able to detect quite a bit, right? It may be something like won't be 50%, but around 40 something. We can try one more random vector. Okay, so I leave that as an exercise to you. You take another random vector. It is likely that it will detect some of the same faults. Okay, for example, if I take 1111, see it will detect A0 also. Okay, so like that, um, but there will be a few unique faults that it will detect. So if you take, let us say, about 3 or 4 random vectors together, they may detect maybe about maybe it will go up to 11 or 12. Okay, so selecting more random faults, random tests can increase fault coverage. Okay, we don't want to consider every test. That is not correct. Right? We have to choose some small subset of these test vectors. So in this example, there are 16 possible test vectors. So a reasonable number is maybe around maybe maybe 10%, 20%. So 3 or 4 test vectors, let us say, is reasonable. That may give us a fault coverage of, let us say, around 12 out of 80. Okay, maybe 66% coverage. Okay. The remaining we have to manually do. Okay. So let us pretend that none of them have covered even zero. Okay, what is even zero? I think this is even zero. Okay. So if this is even zero, in order to activate that fault, we'll have to put a 1 here. Okay. So a good circuit has a 1 and a faulty circuit has a 0. Okay. So we refer to that as D. You remember?
Yes, sir.
In order to put a 1 here, if you work backwards, you will have to put a 0 here. So that is called justification. How do you justify putting a 1 here? We can do by putting a 0 here. If I put a 0 here, this will become a 1, and this will also become a 1. And so will this be. This will also be a 1, and this will also be a 1, and this will also be a 1. So this is justification and making sure that we have simulated all the whatever we can. Okay. All the other places still have what is called as x. X means at this point of time we don't know what that value is. Okay. We have made x a equal to 0 because we wanted to activate this fault. B is x, C is x, D is x, and 1 dot x bar is still x only. Okay. So we don't distinguish between x and x bar. X bar is also treated as x only. Now, in order to now we have to propagate this fault further. Okay. So what should I put here so that I can propagate the fault here?
One.
When will a 1 has to be put, because if I put a 0, then both good and bad circuit will have a 1 here. So if I put a 1 here, and I can justify that 1 by putting a 1 here, and I can justify it back by putting a 0 here. So if I put a 0 here, I'll get a 1 here and I'll get a 1 here. And moment I put a 1 here, I can simulate this and say this will be D bar. D bar means the good circuit has a the good circuit has a 0, but the faulty circuit has a 1. So 0 x 0, that is a test pattern or a stuck at 0 fault on E1 0. So we will have to do this. Okay. And see, 0 doesn't make a lot of sense. 0, when you have to actually apply the tests, we will have to define what x is. Okay, so we have a choice. So we can pick maybe 0 or whatever we want. Okay. Then again we can simulate that, just like we did here. This is called fault simulation. Okay. 1011, after doing fault simulation, the coverage is 7 out of 18. So once we put 0 0 0 0 or something like that, again we can do a fault simulation and see, maybe we luck out and it will also have a few other faults. We are sure that it generates, or either it catches D0 here, I'm sorry, stuck at 0 here, but maybe this guy will also catch a few others. So then you have to repeat this for each of the so what we'll do is, after we pick 0 0 0 0, we can knock off this E1 0. Okay, so this is gone because of the 0 0 0, okay, whatever that was, 0 0 0 0. And if you have chosen all zeros, then this will become a 0 here. Okay, so this will have a 0 here.
Sir,
Yeah,
so is it a standard to use the status of good circuit before the slash and the bad circuit after the slash, or?
yeah. Good slash bad. Yeah,
Oh,
right.
yes. So this
So
order
0,
never changed.
it's always the same order, good slash bad. Yeah.
Okay.
So
Yes.
0 0, if I put, I am getting a 0 here. And if this were to get stuck at 0, it will change. So that means E21 stuck at 0 will also be caught. I think this is also caught. Okay, and I don't know whether anything else will be caught. I don't think anything else will be caught, perhaps. No, maybe B1 will be caught, right? B1 will be caught because if this changes to 1, it will change to 0. So B1 will be caught. But B1 is already caught. Okay. So 0, 0, 0, 0 will catch two more faults. And then we have to pick one more. Okay. And see, this is not an easy optimization problem. Okay. If you, um, there is a little bit of a luck here, right? If we choose instead of 0, 0, if we had chosen something else, maybe we'll get more faults. Okay, or the order in which we select. Okay. So if I had started with A1 and generated a test vector, so little bit of luck is there. Okay. So ATPG tools will start with some random vectors and find out what all the faults these random vectors will catch. Then look at targeted test generation and then fault simulation and repeat till we get adequate coverage. See, adequate coverage means, see, 100% if you target, right? The problem could be it will require too many tests. In this example, it may not be such a big deal, but imagine a very large circuit with lots of inputs and outputs. There is a good chance that it will take too many test vectors, and we can't afford to do so many. So we may decide to stop when we get 96 or 98, something like that. Or the other reason to stop is we are able to prove that a particular particular fault is untestable. Okay? So sometimes a fault could be untestable because I would have explained this in the notes or rather in the class video. See, maybe it is a redundant line. Okay, that wire is redundant, and if there is a redundancy, you can't catch that fault. So I have given many examples, I think, in the video of why a particular fault could be untestable. So if you suppose there are 18 faults here, right? If I pick 1011, I am able to catch 7 out of 18. Okay? But what if, let us say, two of these are untestable? In this example, I don't think that is the case. But suppose in some other circuit, right, I have two of these which are, no matter which test pattern you apply, it will not be caught. Then what people do is, instead of reporting it, like this, they will say it catches 7 out of 16 faults because 2 can never be caught. Okay. So that number looks a little better. So some people will refer to that as a test coverage instead of fault coverage. Okay. So test coverage means the denominator has the set of all detectable faults. Okay. Whether a fault is detectable or not is not such an easy thing to determine in a actual circuit. See, if I give you a very large circuit and I ask whether a particular wire is redundant or something like that, it is not an easy, there is no easy algorithm for that. Right. So ATPG tools may sometimes sort of try it, they don't know that this is an untestable thing. They may not be able to prove. So they will repeatedly try to generate a test vector, and how do they do it? They do it by backtracking. Okay. So in this example, it may start by putting 1/0 and then justify. And in this example, everything worked out fine, right? There was no problem. but it may turn out that I may not be able to propagate it further. So I can say, no, this decision was not a good decision, change it back to one. So that is called as backtracking. So you try some move, right? It's like, when you are trying to play chess or something like that, you try one move and see what it can do for us. And then if that doesn't work, try an alternate move like that, right? So that is how these ATPG algorithms are. And suppose they find that after about 100 backtracks, and each of these will take a lot of time, right? Every time we backtrack, we have to, in a large circuit, there will be a lot of computation, right? So if we are not able to generate a test vector after a certain number of backtracks, we can abort the fault, saying, it's I don't know, I mean, I can't do this, right? So at the end, you will have different kinds of faults. Some are testable, and we have test vectors for them. Some we know are untestable because we can prove that they are not testable. They are either redundant or something like that. Then some are, we don't know what it is. So I am not able to generate a test for it because it just takes too long. So those are called aborted faults. If we do find a lot of aborted faults, we can try increasing the amount of backtracking. Okay, we can see, okay, I'll give you more time, see whether you can figure it out. And of course, if you are willing to add extra wires, see, for example, if I find that, this particular stuck at 0 or something here is very difficult to detect. Okay. Then one simple thing I could do is I can make this a primary output. Then it is no big deal. I have already found that stuck at 0 fault here because I have made this 0, this has become 1, and it's also a primary output, and I have. So if you are willing to make changes to the circuit, you can improve the coverage. So 100% coverage will be ideal, but due to various things like redundancies and complexity of the circuit, which is not allowing you to generate 100% coverage, often we may settle for slightly lower. Okay. And like I said, it is better to look at test coverage. Okay. So in test coverage, the denominator will not include all these redundant faults, etc. So 100% test coverage may be better to target. Okay. So I think that is basically what we have covered in this week. Okay. Anybody has any doubts?
Sir,
Yeah.
this redundancy, do we have any benefit? Is it something we add
Yes.
deliberately or by
Yes.
chance?
Yes. We can add deliberately. See, for example, we may replicate the same circuit multiple times. Okay, because if one of them has a fault, the other one will generate. See, for example, suppose I have a memory element or something else. I can replicate it 3 times and take the majority of this. Okay, so there is a voting element here. So if 2 or more are 0, we'll take it as a 0. If 2 or more are 1, we'll take it as a 1. So that is known as a voter or a majority voter. So here we have introduced redundancy. Okay, we wanted to store 1 bit, but we are actually storing three, right? It could also be logic. It doesn't have to be memory. It could also be logic. So we have replicated the logic. Okay. In such circuits, there will be plenty of faults which are redundant faults. Okay. We will not be able to detect a fault on that. See here, you can see, right? If there is suppose I put suppose this memory has a stuck at 0 fault here. I'm not sure whether it is so easy to detect it. Suppose I have a let us look at 0 0. Okay. If I apply 0 0, the good circuit will have a 0, faulty circuit will also have a 0. If I apply a 1 1, the good circuit will have a 1, faulty circuit will also have a 1. Right. See that we have done this redundancy in order to tolerate one fault, and if that guy becomes stuck at 0 or something like that, you cannot be able to catch it. Okay, did it answer your question?
Yeah, yes, sir.
Yeah. All right. What else?
Sir, this
In your
stuck at
test,
0,
stuck at 0.
and stuck at 1.
Hmm.
So, what
In this,
usually what's the chances of it happening?
why would it happen? It would happen, for example, see if A is stuck at 0, this output will be stuck at 1, right? The reason
Yeah.
why stuck at 1 faults could occur is one possible reason is there is actually a short circuit between that node and the uh, VDD wire. Okay, so when they laid it out, maybe these wires are running very close to one another, and they could result. When they do the manufacturing, uh, they use acids to remove the extra metal between the two nodes. Okay, so initially, the whole thing will be metallized, right? And then they will remove wherever they don't want the wire, and if they don't remove enough wire, then that will cause a short circuit. And who knows, VDD and that wire, that node may actually be short circuited.
Yes, sir. And sir, this automatic test pattern generator,
Mm.
is it a hardware or software?
It's a software. It's a software. So the software will read the description of the circuit. Okay. So I can tell the software how these wires are all connected, how the inputs are connected to NOT gate, etc., etc. That is known as a netlist. Okay. So it will read a gate level netlist, and it will do all this whatever we did manually. It will generate all the list of single circuit faults. It will eliminate, it will do compaction and get you a smaller fault. All this is automated. There is a tool for doing all this, right? And then it will also generate random test patterns and do fault simulation. And finally, it will start doing ATPG, and it will try to give you the minimum number of test vectors. But there is no guarantee. There is no guarantee that the number of tests it gave is minimum, and there is no guarantee that that is the best coverage that we can get, because as I told you, there is a little bit of a luck factor involved. So you can try running it a couple of times with different random seeds, and then you may get a slightly different answer. But in a very large circuit, that you may not see any major improvement by running it again. Okay? So remember, when you run deterministic algorithms like sorting, etc., the output is always going to be the same. But when you take these ATPG and all these kind of software, when you run it more than once, you may get slightly different results.
Okay, sir.
Right? Any
Yes, sir.
others? Any other some?
Sir, I have
Hmm.
doubts in two of the lecture videos.
Hmm. Yes.
In lecture 19
Uh-huh.
of week 3,
Yeah. What is the doubt?
it's around 9 minutes. Um, I
Hmm.
think the
You do
in
one
that
thing,
part of the video.
Ashutosh. You ask this to Ashutosh, okay? If he is not able to
Sure,
answer,
sir.
I will answer. Okay.
Sure, sir. Okay.
Because I don't know, I don't have that ready-made. I can't go to that. I mean, I'm too
Yeah, sure.
lazy to go and figure that out. But if you can ask that question as a, without going to the video, I can try. Or ask Ashutosh.
Yeah, sure, sir. Okay.
Okay. Any others? You are also welcome to send it to Ashutosh by WhatsApp or something. If he is not able to answer,
Okay.
he will forward it to me and I will send it.
Sure, sir. Okay.
That's it. Okay. I'll
Yes.
see you guys next week.
Yes, sir.
Bye.
Thank you, sir. Hello, sir.